We use the internet every day and just expect it to work. But behind your favorite apps and websites, there was a point not too long ago where the entire system was about to break. I mean, literally hit a wall. This is the story of that crisis and the incredible revolution that it sparked. And it all really boils down to this one question. Why did the absolute giants of the tech world, Google, Amazon, Facebook, companies with all the money and engineering you could ask for, why did they look at the databases that existed and say, yeah, that's not going to work for us. We have to invent our own? The answer to that question, well, it changed pretty much everything about how data works. So to really get why this was such a revolution, you first have to understand the old way of doing things, the world before the wall. For a really, really long time, there was basically one game in town. If you had data, you put it in what's called a relational database, or an RDBMS. These things were the undisputed kings. They were reliable, structured, predictable. They brought a beautiful sense of order to the chaos of information. But then the internet exploded, and suddenly the old king was facing problems it just wasn't built for. First, these databases demand that you define the exact structure of your data ahead of time. That's tough when you've got a fire hose of unpredictable data coming in. They also weren't great at handling the messy, unstructured stuff like comments, photos, and videos. And the biggest problem? To make them more powerful, you had to buy a bigger, badder, more expensive computer. That's called vertical scaling, and it gets ridiculously expensive fast. On top of all that, the way these databases stored data often just didn't jive with the way modern programming languages like to work. And if you need a smoking gun, this is it. This research from the legendary computer scientist Michael Stonebreaker is just jaw-dropping. He looked at what these high-performance databases were actually doing, and he found that less than 7% of their time was spent on what he called useful work, actually getting you your data. The other 93%? That was all internal bureaucracy, managing memory, locking data, writing logs. It's like having a supercar where 93% of the engine's power is just used to keep the engine itself running. It was shockingly inefficient for the new web-scale world. So the writing was on the wall. The tool that had been the perfect hammer for every nail for decades just wasn't cutting it anymore. The whole idea of a single, one-size-fits-all database was officially dead. And when an idea that big dies, it creates a vacuum. And into that vacuum rushed a new philosophy. A revolution that wasn't about one new king, but about having lots of different tools for different jobs. And the name for this whole movement? It's kind of funny. It was practically an accident. Back in 2009, a few developers in San Francisco were putting together a meetup about all these new kinds of databases. They needed a good, punchy hashtag for Twitter, right? They searched for a few things, and NoSQL was short, catchy, and not really being used. They picked it. And just like that, a name was born and a movement had its banner. Now, this is super important to get right. The name NoSQL is a bit misleading. It doesn't mean we're saying, no, we hate SQL. Not at all. A better way to think of it is not only SQL. It's this big umbrella term that basically says, hey, for the kinds of problems we're facing today, we need more tools in our toolbox than just the old relational database. And you can really see the difference in philosophy when you put them side by side. The old relational world forces you to have a perfect, rigid structure when you write data. The NoSQL world is way more flexible. You can often figure out the structure when you read the data. Relational databases scale up. You buy one giant, powerful machine. NoSQL databases scale out. You just add more and more cheap, commodity machines into a big cluster. And this last one is absolutely crucial. Relational databases chase perfect consistency, while NoSQL databases often make a trade-off for something else. We'll get to that. And like I said, who was driving this whole thing? The companies with the biggest headaches. Google was drowning in data for its search index, so they had to invent Bigtable. Amazon's e-commerce platform needed a database that could scale to the moon and back, so they created Dynamo. Facebook needed a new way to power its massive inbox search, and that led to Cassandra. This wasn't a trend, it was a solution born out of pure necessity. Okay, so NoSQL isn't just one thing. It's more like a big, diverse family of tools. And each member of the family is really good at one particular kind of job. Broadly speaking, there are 4 main types. You've got key-value stores, which are super simple, basically a giant dictionary, perfect for things like a user's shopping cart. Then you have document stores, which are awesome for messy, semi-structured data, like a product catalog, where every product might have different specs. Column family stores, like the one Google built, are designed for absolutely massive datasets. And finally, you have graph databases, which are built from the ground up to understand complex relationships, like a social network. So we have all these new specialized tools. But it turns out they all have to obey a fundamental law of physics for computer systems, a law that forces you to make a really, really tough choice. Some people call it the impossible triangle. See, in any system that's spread out over a bunch of computers, there are three things you desperately want. First is consistency. That means everybody everywhere sees the exact same, most up-to-date data at the exact same time. Second is availability. That just means your website or app is always online, ready to answer requests. And third is partition tolerance. That's a fancy way of saying your system doesn't fall over and die if the network cable between two of your data centers gets cut. You want all three, right? Of course you do. Well, here's the catch. It's called the CP theorem, and what it says is devastatingly simple. In any distributed system, you can pick two of those three things, but you can never, ever have all three. Now, think about that for a second. In the real world, networks fail. Connections drop. It's not a question of if, but when. So that partition tolerance thing, it's not really a choice. You have to design for it. Which means the real, agonizing trade-off that every single large-scale system has to make is this. Do you choose perfect consistency, or do you choose 100% availability? You can't have both. And that brutal choice leads directly to the final and maybe most radical idea that powers so much of the internet we use today. The old-school relational databases lived by a set of promises called ACID. It's an acronym that stands for things that guarantee every transaction is perfect, isolated, and durable. It's a promise of absolute correctness. But many of these new NoSQL systems embrace a totally different philosophy, one called BASE. It stands for basically available, soft state, and eventually consistent. It's not about perfection, it's about being pragmatic. And that brings us to the core concept, eventual consistency. It's a simple promise. It says, look, for a split second after you post that photo, your friend in another country might see an older version of your feed. Things might be briefly out of sync. But, and this is the key, it promises that if everyone just stops making changes for a moment, the system will eventually catch up and everyone will see the same thing. It chooses to be available over being perfectly, instantly consistent. Which leaves us with a big, central question of this whole story. In a world that runs 24/7, a world where your service being down means you're losing money and users every second, is that old ideal of perfect, instantaneous consistency always worth the price of potentially going offline? For a huge chunk of the modern internet, the architects and engineers decided the answer was no. And that decision, that trade-off, is exactly why the web works the way it does today.